What's up, fellow students, and I'm surprised you made it this far. Anyways, let's just jump into the lesson. So first, let's start with a brief history of the discovery of these laws. The laws of motion began with the one and only Sir Isaac Newton. You know, the guy who developed a ton of theories for gravitation back in 1666 when he was just 23 freaking years old. Well, anyways, 23 years later, he was walking down the street when he saw a car moving and thought, wow, that car is actually moving. How though? And tada, that's a brief history of the three laws of motion. Disclaimer though, this is just a fun visualization of how the three laws of motion came to be. The focus of this video is to help you understand what the laws of motion are and how we can apply them to the real world. Now that I got your attention, let's go to the real topic.
For the first law, it states that an object that is at rest will stay at rest, and an object in motion will remain in motion, unless compelled to change its state by the action of an external force. This is what we normally call as inertia. It literally means that if there is no net force acting on an object, then the object will maintain whatever its current state is. If the object's velocity is zero, then the object remains at rest. If an external force is applied, then what do you think will happen? That's right. The velocity will change because of that force. That's why the first law is called the law of inertia. For the second law, the law of acceleration. Pretty serious, right? Well, this one is actually easier. It explains how the velocity of an object changes when it is subjected to an external force. So basically, the force is equal to mass times velocity. And remember that, folks. Also, there's actually a formula for this. Force is equal to mass times acceleration. For an external applied force, the change in velocity depends on the mass of the object. A force will cause a change in velocity, and likewise, a change in velocity will generate a force. So for your information, this equation works in both ways. For the last law, the law of interaction. And no, we're not talking about dialogues and conversations. We're talking about motion. Duh, it states that for every action, there's an equal and opposite reaction.
Now fellas, keep in mind that the key phrase for the law of interaction is, for every action there is definitely an equal and opposite reaction. And in Nathan's case, the reaction is quite a painful one. Now, walking. Now, hear me out. When you're walking, you're actually applying force to the ground. And in doing this, the ground also applies an equal force onto your foot in the opposite direction, pushing you forward. Now, if you think about it, Iron Man is flying because of the law of interaction. Because the suit acts like a rocket, and the equal and opposite reaction plays an important role here. The fuel exhaust that's forced out of the tech can propel the user to the direction they're facing. Now, why don't we try bouncing a ball? Again, it is pushing the ground, and because of the equal and opposite reaction, the ground pushes it back, allowing the ball to keep bouncing and bouncing. And that, fellas, is the law of interaction. With that, it is summary time. Now, always remember that the law of inertia is about the object that is at rest will stay at rest, and an object in motion will remain in motion unless compelled to change its state by an action of an external force. Now, for the law of acceleration, the force of an object is equal to its mass times acceleration. And for the last and final law, the law of interaction, for every action there's an equal and opposite reaction. Now get out of here and good luck on the final exam, fellas.